Okay, in this video we're really going to get to the meat of how aldehydes and ketones react with oxygen nucleophiles. We're going to talk about two kinds of nucleophiles, hydrates and alcohols. Water forms hydrates, alcohol forms acetals, and hemiacetals as intermediates. So let's define some of these terms here. Water reacts with a carbon-oxygen double bond in the same way that it reacts with a carbon-carbon double bond. You add a molecule of water across the carbon-oxygen double bond, you have the hydrogen that goes to the less substituted atom, in this case oxygen, the OH goes to the more substituted atom, and the mechanism, at least under acidic conditions, is very similar to what we've already seen, right? So let's say that you take acetone, you treat it with water in the presence of an acid catalyst, right? You form a hydrate, right? But the ketone or the aldehyde that you start with is by far much more stable than the hydrate. And so these hydrates generally are very, very difficult to isolate. And in this class, we're not ever going to talk about isolating hydrates or using them to do anything useful. We're just going to understand the reactions to make hydrates so that we can understand future reactions a little bit better, right? So let's look at two possible mechanisms very quickly. Remember in the previous video, we said that you always want to ask yourself, what's going on? And the first thing you want to ask yourself is, are you under acidic conditions or are you under basic conditions? Under acidic conditions, right, we're always going to protonate the oxygen of the carbon-oxygen double bond first. That's going to generate the more substituted carbocation, right, because we have a positive charge on oxygen, right, but now we have a resonance structure of that, which gives us a tertiary carbocation. So not only is it tertiary, it's also resonance stabilized. And that's a really good nucleophile for a molecule of water, which is our solvent. So water is not a great nucleophile, but if we generate a stable carbocation, then we can have our water molecule attack, right? And so now all we need to do is lose a proton. And that gets us to our hydrate. So notice under acidic conditions we have a proton transfer step first, we have a nucleophilic attack second, and we have a proton transfer step third, right? We transfer a proton to the oxygen, which makes the carbon more electrophilic. It gets attacked by the nucleophilic water molecule to generate this protonated product, which can then lose a proton to give us our hydrate. What would happen under basic conditions is actually a little bit more straightforward. We have acetone, in this case, reacting with hydroxide and water. Hydroxide is a good enough nucleophile that the electrophile doesn't need to be activated. We just attack right off the bat. We break our pi bond. We get an O minus here, and we get an OH. And then we have water present, which can supply a hydrogen to that O minus. So a lone pair on the oxygen accepts the proton to regenerate a hydroxide molecule, give us our hydrate that we got in the previous case. So hydrates can be formed under acidic or basic conditions, but they will not predominate in the equilibrium. Let's talk about a useful reaction. That's acetal formation. This always is going to happen under acidic conditions. We use an acid catalyst, usually toluene sulfonic acid, which we abbreviate TSOH, or sulfuric acid. And we usually use a large excess of the alcohol. You need at least two equivalents, but for all reactions that we're going to talk about, we use it as a solvent, which helps shift the reaction toward the acetal product. The mechanism of the acetal formation is going to follow the same steps as hydrate formation, and then we're going to add a few extra steps. So whenever you're trying to propose a mechanism, right, first thing that you always do is ask yourself, is this acidic or basic? Hopefully you figured out that it's acidic. Then you want to remember, what are the first two steps? Proton transfer, nucleophilic attack, and then we're going to try to propose sensible steps that go from that product all the way to our acetal, right? All right, so let's try to do that for this reaction. Let's try a simple case. Let's say our reaction is acetone. Our overall reaction is acetone, and we're going to treat it with toluene sulfonic acid and methanol to give an acetal where we have two OCH3 groups bonded, and we also form water as a byproduct, which you don't have to include because remember, we only care about the organic product. So we're forming an acetal. So when you mix together a strong acid in methanol, it donates all of its protons to methanol. So anytime we need H+, if we need H+, we're going to get it from protonated methanol, or whatever your solvent is. In this case, it's methanol. The protons are going to come from the protonated solvent. If you want to accept anything that's going to accept an H+, is going to be the solvent. There's lots of solvent molecules available. And so your acid in any step is going to be methanol, and your base in any, your acid in any step is going to be protonated methanol. Your base in any step is going to be methanol. Let me show you what I'm talking about. So let's say we start with acetone, right? And we need, the first thing that happens is we protonate the oxygen. We said proton transfer is always the first step under acidic conditions. So we're going to use protonated methanol to transfer that proton, because that's the source of protons that we have in this reaction. So we get a proton from methanol, we break that bond, and we got our protonated guy here. Next step is nucleophilic attack. Methanol is going to attack that carbon. Remember, we could draw a resonance structure for this that places a positive charge there. So we're going to attack here, and in order to avoid 5 bonds at carbon, we're going to break that pi bond. So now notice what we have here. We have a single bond to an OH. We don't have that charge anymore. We have an OCH3 on this side, and that's still protonated, right? It brought its hydrogen with it, so we have a positive charge there. So that's our nucleophilic attack, right? And just like the mechanism for hydrate formation, now what we're going to do is we're going to transfer a proton away from this molecule. And remember, we said anytime we need to accept a proton, we're going to use the solvent to do that. So methanol is going to accept the proton. That bond's going to break. And so we get something that looks like our hydrate product, except instead of 2 OH groups, now we have an OCH3. We're going to call this a hemiacetal. It's half of an acetal. So this last step to make the hemiacetal is also a proton transfer step. So to make a hemiacetal, you do a proton transfer from protonated solvent, nucleophilic attack by the solvent, and then proton transfer back to the solvent to regenerate your protonated solvent and also generate your hemiacetal, right? But remember, our product had 2 OCH3s here, so we need to get rid of this OH. The best way to do that is to turn it into a good leaving group, so we need another proton transfer step. Anytime we need to accept, this guy needs to accept a proton, it's going to do it from the protonated solvent molecule, right? So the oxygen is going to accept that proton. And now we took something that was a bad leaving group and turned it into a good leaving group, so that has a positive charge. We have our OCH3 here. Now, instead of a nucleophilic attack, we have a leaving group leaving. So water leaves. That gives us a really nice, stable carbocation, which can undergo nucleophilic attack by the solvent, right? We have lots of methanol around, which can act as a nucleophile if it encounters a sufficiently stable carbocation. That gives us something very close to the structure of the product. We have an OCH3 here, but it still has an H on it, and we have an OCH3 here. And so the last final step is a proton transfer. So to get to the acetal, we need to get rid of this proton. Solvent will accept it. Solvent is always shuttling these protons back and forth. So the last step is solvent accepts that proton to give us our acetal product. So we have 2 OCH3 groups on here. Everybody's happy. We went from ketone to acetal. We did that in a series of 7 steps, right? Proton transfer, nucleophilic attack, proton transfer to get a hemiacetal, then proton transfer, leaving group leaving, nucleophilic attack, and proton transfer to get to our acetal product. Every single one of these steps is an equilibrium, right? And remember, we can shift equilibria by Le Chatelier's principle. So generally what we do is we use a large excess of our alcohol, in this case ethanol. So if you have a large excess of products, that's going to shift the reaction. Or sorry, if you have a large excess of reactants, that's going to shift this towards the acetal. So in that case, we can isolate these acetals. Even though the reactants are favored at equilibrium, we can get a large we can run this reaction 99% yield by Le Chatelier's principle, and we can also remove water, which is also going to shift the reaction toward the product side. And since this is an equilibrium, we can actually reverse the equilibrium. So instead of using a large excess of the alcohol, if we decide to use a large excess of water, that shifts the equilibrium back to the ketone stage, right? If we go back a slide, if we add a large excess of water in the presence of an acetal, we shift back to the ketone. So we can move this equilibrium any direction that we want to, depending on which conditions that we decide to choose to run the reaction at. Okay. The last thing we're going to talk about is cyclic acetals, which are very useful. And what we're going to use these as protecting groups, right? So if you have a ketone, you can protect it as an acetal, and then, just like we just talked about, you can reverse that equilibrium to get back your ketone. What's nice about cyclic acetals is you have two alcohols in the same molecule, and so they're going to close down to form a cyclic acetal where you still have two molecules of an alcohol that added to your carbon. They just happen to be in the same starting material. Let's talk about the mechanism quickly. Okay, so if we look at the reaction on the previous slide, right, we had acetone, and that's going to react with ethylene glycol in the presence of an acid catalyst. So just like in the methanol example, the proton is always going to come from protonated ethylene glycol, and the base is always going to be the solvent, in this case ethylene glycol. So in the first step we need a proton transfer. So what we're going to do is, the first thing that happens, which I didn't actually draw, is that in the presence of acid, ethylene glycol is going to accept all those protons, right? So anytime we need a proton, that's going to come from protonated solvent. So we have a proton transfer. That gives us our activated carbon-oxygen double bond. Now this guy's electrophilic. We have a nucleophilic attack step. So I'll abbreviate that Na. The nucleophile is our solvent. One of the two OH groups is going to attack. It's going to attack this carbon, and in so doing break the pi bond. So now on this carbon we have an OH on one side. We have an O, CH2, CH2, OH, right? And this still has a proton on it, so that's positively charged. We need to get rid of that proton, so the last thing that happens to get the hemiacetal is a proton transfer. That's going to go to solvent. So we're going to accept that proton. So the hemiacetal now looks like this. We have O, CH2, CH2, OH, and we have an OH over here, right? So we had the same first three steps. Now we have a proton transfer from solvent again. From protonated solvent. We need to protonate this OH to make it into a good leaving group. It accepts a proton. We break that bond. So now we get this guy, which then, so then we have a leaving group leaving step, leaving group. That gives us our carbocation, and this is where the mechanisms sort of diverge, right? So in the previous acetal formation, right, we had a carbocation that gets attacked by another solvent molecule. Well, now we have a nucleophile that's attached in the same molecule, so we get intramolecular nucleophilic attack. So that's a nucleophilic attack step. That gives us a cyclic product. So we have this oxygen is this one, CH2, CH2, oxygen, and that is positively charged. And then to generate our acetal, we need a final proton transfer step back to a molecule of solvent. So then we accept that proton. That becomes a lone pair. And at the end of the day, we have our cyclic acetal. So it's the same series of steps: proton transfer, nucleophilic attack, proton transfer to get a hemiacetal, proton transfer, leaving group leaving, nucleophilic attack, proton transfer to get our cyclic acetal. So just like I mentioned previously with acetals, cyclic acetals are really nice. We can put them on in the absence of water, or if we add a large excess of water in an acid catalyst, we can take them back off again. So we can use these as protecting groups for carbonyls, mostly and just for ketones and aldehydes. So ketones and aldehydes form cyclic acetals. So if we don't want this carbon to react, so this carbon is very electrophilic. This carbon is not as electrophilic because it doesn't have the resonance structure that places a positive charge here. We can add nucleophiles to this carbon, not as easily to this carbon, especially under basic conditions. So let's say we wanted to make this compound. What we would do is notice that we have an ester here. We want to turn that to an alcohol, but we don't want the ketone to react. So we want to react a nucleophile with just the ester. What we do is we first protect it as an acetal with acid and ethylene glycol. So that forms the cyclic acetal, which we can then reduce with lithium aluminum hydride. But notice that in the previous case, if we added lithium aluminum hydride to this molecule, it would reduce the ketone and the ester. But now we protected the ketone, so our product is the primary alcohol from reduction of the ester, but we haven't touched our cyclic acetal yet. So if we add dilute acid, we take off our acetal, we reverse the equilibrium back to the ketone. So we've protected the ketone through this very strongly basic and strongly nucleophilic step. So to summarize, ketones and aldehydes only undergo acetal formation when we mix them with a large excess of alcohol in the presence of an acid catalyst. The mechanism of acetal formation is always going to be 7 steps, and make sure you're keeping track of those proton transfer steps. Every step is reversible, so if we use a large excess of alcohol, we shift toward the acetal. If we use a large excess of water, we shift toward the ketone.